everyone. My name is Vincent, and I'm working on my PhD program with Dr. Butash in shock physics. So the research, our research is focused on the shock behavior of cemented tungsten carbide under shock wave loading to 100 GPa. And today I will give you a very brief overview of the research and the results that we have obtained so far. The overall objectives of our research is to better understand the structure of shock waves in the cemented tungsten carbide and their associated thermodynamic equilibrium states when it's shocked to when it's under shock wave loading. So we're going to determine the ergonial elastic limit for tungsten carbide with cobalt binder and establish the ergonial relationships in the shock speed versus particle velocity, and also in the longitudinal stress versus volumetric compression plane. So the approach for achieving this goal is by conducting the transmission wave plate impact experiments. And we're also going to quantify the evolution of elastic moduli, which includes the longitudinal bulk and shear moduli in the shock compressed tungsten carbides. To achieve that, we need to make the in situ sound speed measurement in the shock speed tungsten carbide. And the last part of our research is focused on the development of a thermomechanical framework that describes the shock response of the cemented tungsten carbide under shock wave loading to 100 GPa. The materials that is being studied in our research is the cemented tungsten carbide. Is the cemented tungsten carbide containing 3.7 weight percent of cobalt binder and a 6 weight percent cobalt binder. There are two grades of tungsten carbide. So these are manufactured by powder metallurgy, where the tungsten carbide ceramics powder are mixed with the cobalt metal and then compacted in a die and then sintered in the furnace. So before each experiment, those samples will be characterized by ambient density and sound wave measurement. So this is the diagram for the experimental configuration for the first set of experiments. The impactor is bounded to the projectile and then travel through the gun barrel, hits the target on the right. The interface of the sample and the window, which is indicated by the orange block and the light blue block, the particle velocity at that interface will be monitored using laser interferometry to get the shock wave loading profile. Depending on the desired peak stress level, we're going to use either a gas gun or a powder gun in our facility. The recorded shock wave profile is shown as the red curve in the figure on the left, where we can see there are three different stages. The first stage, if you can see the cursor. So the first stage is the elastic wave, which is represented by this small jump. The amplitude of this jump is referred to as the ergonial elastic limit, corresponds to around this point, or just the HEL. After the HEL, it's an elastic plastic hardening ramp. And then finally is the plastic wave, which is represented by very large jump. To analyze the shock wave profile, we need to make some assumptions. For example, we assume the tungsten carbide is elastic, perfectly plastic, solid, and also the rate dependence is ignored in the analysis. So the shock wave profile will be simplified as a simple two-wave structure represented by the dashed black line. And then the shock wave profile will be used through the very well established impedance matching technique and the Rankin-Ergonial jump relationships to determine the immaterial quantities, such as the longitudinal stress, the density, and the particle velocity in the shocked tungsten carbide sample. In the figures on the right, we have shown the recorded shock wave profiles for all experiments for both grades, along with their peak longitudinal stress level. The stress level ranges from 9 to 100 GPa for both grades, and the HCl, the elastic limit, measured for the grade containing 3.7 cobalt binder is about 20% higher than that measured for the grade containing 6% cobalt, which means that the increase in cobalt content in cobalt content has decreased its elastic limit. The figure on the left shows the Pogoniod relationship for both grades in the shock speed versus particle velocity plane. The red and the blue symbols represent the two grades in our research. The straight lines from bottom left to top right represents a linear USUP relationship. Such linear USUP relationship indicates the material has reached what is called a hydrodynamic equilibrium states, which means that the material, the shear stress carried by the material is very low compared to the overall pressure, so that the material almost low hydrodynamically. But for ceramics possessing a substantial amount of shear strength, such state will not be achieved at low stress level. So to obtain such linear USUP relationship for tungsten carbide sample, we have to make we can only use the highest two stress levels data points, and where the ratio of the shear stress and the pressure is very low to negligible. And also we assume that the linear USUP curve intersects the y-axis at the ambient bulk sound speed, represented by these two data points. So for the data points on the left of the figure, they fall into the category of strength dominated region, which means at this point, the shear stress carried by the sample is still comparable to the pressure, which means that the strength is dominating the shock behavior. That is why the measured shock speed is more towards the longitudinal sound speed instead of the bulk sound speed when the particle velocity is very low. As the stress level goes to a very high level and reaches the hydrodynamic equilibrium states, the shear stress is almost go to zero. That's why when we extrapolating the data points, we intersect the y-axis to the bulk sound speed as the particle velocity goes to zero. The next set of experiments that we did is to measure the sound speed in the shocked tungsten carbide sample to get the evolution of the elastic moduli. There are two configurations that we use in this set of experiments. One is called the front surface impact, and the other one is called the release wave overtake experiments. The first one has a more accurate measurement, but the stress level achievable in this configuration is limited to only less than 30 GPa. So for stress higher than that, we need to use the overtake configuration. The measured wave profile are shown in these two figures, where we have conducted 3 low stress experiments using the front surface impact and 5 high stress experiments using the release wave overtake. The black arrows on the curves represents the release of the represents the arrival of the release wave, which travels at the longitudinal sound speed sound wave. From that, using that information, we can get the sound speed in the shock compressed tungsten carbide sample. And in this figure, the red symbol represents the measured sound speed, and the blue symbol represents the bulk wave speed we obtained using the third order Birch-Moynihan equation state. They're all plotted as a function of Pavonian stress, which is also the longitudinal stress. With those two quantities, we can get the longitudinal bulk and shear moduli using the relationship on the right. So if we look at the shear moduli obtained from the experiment, so the evolution of shear modulus as a function of Pavonian stress are shown in the figure on the left. The blue symbols represents the theoretical shear modulus value as a function of pressure given by the Steinberg-Guenin model. This model assumes that there's no damage accumulated in the material. However, if we look at the experimentally measured shear moduli using the sound speed, which is represented by the red symbol, there are a large discrepancy. This so first of all, if we look at the low stress data, the measured shear moduli is larger than the theoretical volume value. This is because at this at the shocked state, the microstructure is consolidated under compression, which makes the shear moduli goes higher. And as the peak stress goes higher, the microstructure will be accompanied by mature cracking and fragmentation, etc., like the material damage, which will lower the shear modulus, which is also not accounted for by the theoretical model. And that's why we see this big discrepancy. The last part of our research, which is the part I'm most proud of, is the development of a finite element method framework that describes the shock behavior of tungsten carbide under shock loading. In this part, we have the deformation gradient tensor has been decomposed into a plastic part and an elastic part. That way, between the reference and the current configuration, we have an intermediate configuration. And the power conjugates we used in this framework is the Mendel stress and the logarithmic strain expressed in those two expressions. So the Mendel stress and the logarithmic strain are expressed, are quantities in the intermediate configuration. The reason why we use those two quantities is that the volumetric and the deviatoric response of the material will be decoupled so that we can model the pressure dependence and the hardening effect separately and then add them back together. So in the simulation, we did a coupled, like fully coupled thermal mechanical analysis. For the mechanical part, the volumetric response is modeled through the complete Miller-Bernisen equation state, where the theta in this equation represents the temperature. So the first term is the isothermal pressure as a function of volume. And the second term represents the pressure increase due to temperature rise. The K theta naught and the K prime theta naught in the equation represents the bulk modulus and its pressure derivative at ambient state. For the deviatoric or the hardening part, this is the hardening equation that we used, which incorporates a power law, strain hardening, and a Cooper-Simon type of strain rate hardening, and also thermal softening. I would like to mention that all the parameters are fixed during the simulation, like for all the experiments, except for the rate sensitivity coefficient M. We have taken the rate sensitivity to decrease as increase in pressure, so that we can capture the wave profile better. And the M in our simulation goes from 4 to 2 as the pressure increases to 100 GPa. And the thermal part, for the temperature evolution, we get that through solving the energy balance equation, where on the left-hand side, the second, third, and the fourth term represents the temperature contribution from different sources. It's plastic work, elastic work, and the last one is the viscous dissipation. So by calibrating the model parameters, we are able to fit the measured wave profile in the transmission wave experiments pretty well, especially in the elastic wave and the plastic wave speed, also the elastic plastic hardening part and the peak state. There is some discrepancy at the unloading part. That is because prior to the arrival of the release wave, the material is broken, but it's still held together by the pressure confinement. When the release wave arrives, the broken material or the pulverized material has no longer like confined by the pressure because the pressure is released. So the material is able to flow at a lower pressure confinement. And this deformation physics is not included in our current model, but will be taken care of in the future work. So yeah, in summary, we have successfully determined the Lagrange elastic limit for both grade and established the Lagrange relationship for both grade as well. And also we investigated the evolution of the elastic moduli as a function of pressure. And then from the comparison with the theoretical value, we can see what is we can have some insights into what does the damage look like inside a sample. And we developed this finite element method framework to capture the shock loading behavior. And that's all. Thank you. Thank you.
Good question. So your modeling results are amazingly accurate, right?
Thank you. Yeah.
And you have like what I understand, you started with deformation gradient and you had a rather simple hardening law, maybe it was subsystem dependent, your hardening laws, maybe it was system. So my question is the fitting parameters for your hardening laws that you need to do. So did you fit it from these data, or where did you get the data to establish your fitting parameters? And is this just how good it fits, or did you do it on a separate set of like quasi-static data and then come back? Or how did you get those parameters?
Oh yeah, so actually there are already some studies that uses, so let me just pull up. So if we look at this hardening equation, right? Actually for the string hardening and string rate hardening, people have been using that to model tungsten carbide in their work. There are some work that's been done in Caltech. They have used this
just power law.
Yeah, just power law. Yeah, but they don't have the complete equation state, and they don't have the thermal softening. So in general, we go from there because they have established, so they have reported some of the parameters. So we just go from there and do some more tweaking until the wave profile matches our reported result. Yes. So it's not like we just go in there and choose parameters arbitrarily. We just go from what they have reported and then make some slightly modifications.
Same lines. Not sure if I understood correctly, but initially when you were talking about like impedance matching and kind of looking at actual burnout relationships, you mentioned that your assumption is that material is elastic with plastic.
Yes.
How does that, then how do you put that in contrast with assuming a straight hardening behavior?
Yeah, so the reason, so first of all, the reason why we're doing this modeling is because when we're doing the impedance matching, we have to assume it's elastic, perfectly plastic, and we don't consider the rate dependence, so that we want to have a better model. That's why we are incorporating all those things in this model, so we can get a better better idea what is really going on. And if I don't have enough time to present all the results, but if we look at the results from the simulation and the experimentally measured data using impedance matching technique, the values are different, but not too much.
So very drastically different types of mechanical response.
I'm sorry, what?
So, but perfect plastic response compared to strain hardening responses are very kind of drastically.
Oh, yeah,
Like response of material that we're looking at. So
right.
I don't know how in terms of like putting the experimental results now in comparison with the final element results, would that introduce some errors when you compare?
Yeah, there will be some errors for sure, because like you said, they are like very different material behaviors. But we know that the impedance matching technique is like I would say like flawed because of those assumptions, right? Because we I mean for metals we can make those assumptions like it's elastic, perfectly plastic, given that the shock pressure is very high. But for tungsten carbide, making that assumption is not exactly accurate. So we have to see how inaccurate those impedance matching technique and those assumptions are. And that's by comparing the simulation and that data. But so,
And one more question, so there are some reports in the literature on pressure-induced shock, pressure-induced phase transformation of tungsten carbide. Did you see any evidence of that, or do you have like significant tungsten carbide as well?
I'm sorry, the see what?
Pressure-induced phase transformation
Oh.
from like hexagonal to cubic for tungsten carbide.
Oh, really? I haven't seen any paper that reports the phase transition in tungsten carbide. I mean, that must have been very high stress level, right?
Yeah, I can't remember the stress level of the topic.
It-
Something
as-
to consider.
Okay, as far as I so based on my understanding, because the shock stress in our case is still considered low because we still see that two-wave structure. It's not even an overdriven shock, so I wouldn't anticipate any phase transition at this stress level.